Hello students, a very warm welcome. Today we'll be beginning a new topic, chemical equilibrium, and we'll be introducing you to it. Alright, so let's get started. The first slide over here, there are two sorts of reactions, guys. Right? Two sorts of reactions. One is irreversible, right? And the other is reversible. Right? If we talk about irreversible reactions, irreversible reactions proceed only in one direction. For example, if I take A plus B forming C plus D, right? This proceeds only in one direction. So these reactions are generally very fast, right? And once they are completed, right, there is no tendency of going back, hence they are irreversible, right? They proceed in one direction only, that is the forward direction, that's it, right? Certain examples of irreversible reactions are precipitation reactions. So you might have seen that when NaCl, for example, is introduced to an aqueous form of AgNO3, both in aqueous form, right? A precipitate of AgCl is formed immediately as both come in contact, right? NaCl and AgNO3, right? So AgCl, this white precipitate forms very quickly, and this reaction is irreversible, right? It proceeds to complication almost immediately, right? So this is the first example. Precipitation reactions in which a precipitate are formed are generally irreversible, right? Apart from that, neutralization reaction, right? Neutralization reaction, because in neutralization what happens is an acid and a base, right? Acid and a base, because acid has H plus ions, right? And base has OH minus ions. So they combine very quickly and a lot of energy is released. So these reactions are highly exothermic, right? Because of which, because a lot of energy is released from the system, what happens is system becomes very stable. Hence, these neutralization reactions also proceed forward very quickly. So when an acid and a base reacts, the reaction occurs very quickly and it's almost irreversible, right? The third sort of reaction is reaction in open vessel, right? Reaction in open vessel when one of the products is gaseous, right? So what happens is, for example, let's say if we have CaCO3 and we heat it, it dissociates into CaO and CO2, right? Gaseous. Now, if you have an open vessel in which this reaction has taken place, the CO2 will escape out, the gas will escape out, right? So that's why it will never be able to return back in the backward direction, right? I hope you understand this, guys. I'll move on. Reversible reactions, on the other hand, guys, they proceed in both the directions, right? So, for example, most of the reactions are generally, when you are studying organic reactions, most of the times, most of them will be because over there, even the neutralization reactions occurring between acid and bases won't be very strong reactions. They won't be very exothermic in nature. So generally what will happen is most of the reactions would be reversible in nature, right? So if you have N2 and O2, right? N2 and O2 react to form 2NO, gaseous. So if this is taking place in a closed vessel, right? The gas is not able to escape out, then what will happen is this 2NO will again dissociate to form the original reactants, right, which are N2 and O2. Similarly, if you have PCl5, right, this PCl5 when it's heated a little bit, it gives PCl3 and Cl2, right? But at the same time, what will happen is the products will also keep combining and move in the backward direction, right? Move the reaction in the backward direction and form the reactant itself, the original reactant itself, right? I hope you've understood this, guys. Moving on, not all chemical reactions proceed to completion, guys, right? Not all chemical reactions proceed to completion. There could be many reasons. For example, two of the most important factors are enthalpy and entropy, right? So the energy of the system must become as low as possible. So two factors play an important role in that. You might be aware of the Gibbs equation, right, in thermodynamics. All right, if you are not aware, we'll be covering it in quite depth, right? So what we know over here is not all chemical reactions proceed to completion, right? Some of them stop in between. For example, at 40%, 50%, 60%, somewhere in between they will stop, right? And when they stop, what happens is there are still reactants present, right? So what happens is these reactants could react, but what's happening exactly is the rate at which it is going forward, the reaction, the products would also be forming at the same, the products would also be dissociating or combining at the same rate to again give back the original reactants, right? Sometimes what will happen is that the tendency to go forward even in equilibrium will be higher and the tendency to return back will be lower, right? But still the reaction won't reach completion, right? Somewhere in the middle, what will happen in general is that they will move forward, but there will also be a tendency to move backward. Or for example, it could be a case where this backward arrow is much more prominent than the forward arrow, right? So I hope you understand these scenarios, guys. So if you take, for example, H2 plus I2 combining 2HI gas, right? This reaction won't complete, right? What will happen is this 2HI will start dissociating and forming the original reactants, right? Similarly over here, this is an organic reaction. This is acetic acid. This is an alcohol, right? So a base. So if it gives this and this, what will happen, guys, is that again this reaction won't reach completion. In fact, it will reach an equilibrium at some point, right? It will reach an equilibrium at some point. This is a reversible reaction. So are these, right? I hope you understand. The very important thing also to note, and we've discussed this in the earlier slide, that the vessel in which the reaction is taking place must be closed. So closed vessel, right? I hope you understand, guys. I'll move on. Next up, so chemical equilibrium, right? Equilibrium in chemical reactions or equilibrium anywhere, guys, is what? So for example, if someone is running on a treadmill, guys, if someone is running on a treadmill, what you see is, you know, they are running, but what exactly is happening, that they are not moving forward, neither are they moving backward, right? You see that they are not moving forward, nor are they moving backward. So on a macro level, right, there is no change, right? But if you go on and say on a micro level, right, if you take a microscope perhaps, right, and see, right, in the solution, are there particles colliding, are there new products perhaps forming? It will be forming, right? On a micro level there are changes, right, but on a macro level there are no changes. For example, let's say if HI, right, in the gaseous form dissociates into H2 and I2, what you'll be seeing is, you'll be seeing that initially what happens is, because of the formation of I2, which is violet in color, you'll see violet vapors, right? But after some time, what you'll see is that although the reactant is not completely finished, right, the reactant is not completely finished, still the intensity of the violet vapors has not increased, right? It has become stable, right? So you are running, right, but nothing is happening. That is a sort of great analogy for a chemical equilibrium process, right? Again, reversible reaction. Equilibrium is a state of a system and it is defined for chemical change, physical change and thermodynamic processes, right? So for example, thermodynamic processes, if we talk about, guys, so if you bring in contact a hot and cold body, heat is exchanged until uh, both have the same temperatures. But when they have same temperature, there is exchange of heat still occurring, but temperature of both the bodies is not changing, right? Chemical change we've already talked about and we'll talk about it a lot. And in fact, in a physical process also, when physically things are not changing, this is again applicable. All right, I'll move on. State of equilibrium means the balance of driving forces. The forces that are taking the reaction forward, they balance the forces that are taking the reaction backward, right? So you might have studied about forces in your physics, right? So if one force is applied like this and an equal force is applied like this, one force is applied like this and equal force is applied like this, the object does not move anywhere, right? So on a macro level, because of this, whatever is carrying the reaction, right, in chemical equilibrium, for example, if it's carrying the reaction in the forward direction, the tendency to go in the forward direction is same as the tendency to come back in the backward direction. All right, I hope you understand this point, right? So the conditions or the factors that contribute for the forward reaction become equal to those factors which are contributing in the backward direction, guys. All right, so reversible reactions, the extent of reaction in equilibrium varies with experimental conditions, right? So for example, if you have CaCO3 and you give it a little bit of heat, right? You don't give it a lot of heat, what will happen is the products will form but at a very slow rate, right? And the reaction won't proceed as fast as you would expect. But if you heat it a lot, right, quickly things will form, right? Quickly, this is solid again, this is gas, this is solid, right? And if you don't allow it to escape, right, then the operational conditions will determine how much the reaction moves forward, right? Or if it's an reversible reaction, how much will the reaction move backward as well, right? So it's the experimental or the operational conditions that define the extent of a reaction in equilibrium, right? How much has the reaction completed before reaching equilibrium, right? Some reactions, they would at 98% reach an equilibrium, right? Some reactions might reach an equilibrium at 5%, right? That all depends on the conditions, right? Conditions and the tendency, right? So conditions could be, right, the concentration, right, the pressure, the temperature. These are very, very important, right? Concentration is moles upon volume, right? So it's again dependent on volume also, because, right, moles is dependent on mass, right? So again, it will be dependent on the mass of the substance taken and all, right? It is very important in industry and laboratories, the equilibrium is favorable in the direction of the desired product. So since it depends on the operational conditions, right, can we fine tune our experiment? For example, you might be knowing that this reaction is used in the preparation of ammonia, right? This is Haber's process. This is used in the preparation of ammonia. So if equilibrium is reached, right, no matter what you do, right, no more of ammonia is being formed, right? So this is disastrous for the industry, right? We want ammonia to be produced, right? That is why the whole system is designed, right? But what we can do over here is we can vary the operational conditions, right? For example, the pressure, the volume, the temperature, the concentration, the moles, right? All these can be varied, and in fact the solvent also, right? So all these can be varied and our desired product can be obtained. The reaction can be pushed in the forward direction, right? This all we'll discuss in this chapter only, perhaps in the time of 2 to 3 lectures, where we talk about Le-Chatelier's principle. Le-Chatelier's principle, right? I hope it makes a lot of sense, guys, right? All right, moving on. Next, so physical equilibrium, right, or thermodynamic equilibrium can be showed when a hot and a cold body is brought in contact, right? They will exchange energy, right? You can feel that one is becoming hotter, one is becoming colder, right? But after a certain time, both of them attain a certain temperature, and it no longer varies, right? Actually, what is happening is the energy is still getting exchanged, right? But on the surface, you cannot feel it, right? On a macro level, you cannot feel it. So this is again a type of equilibrium, right? Chemical reaction taking inside a closed beaker, right? A closed vessel is very, very important, so that the products in any form don't escape, right? For example, a gas can directly escape out, or a liquid can evaporate or something, right? So the conditions must be proper, right? Okay. Moving on, state of equilibrium means the balance. We've talked about this. The two things that are very important over here is that you might have studied this, right? Or you might not have studied this. This is Gibbs-Helmholtz equation, right? For the Gibbs free energy, which is delta G is equal to delta H minus T delta S, right? So there are two, right? If you see this delta H and this delta S, right, they are actually opposing in nature, right? Because this T is taken in Kelvin, right? So this T will be positive, right? It will be above zero, right? Above zero Kelvin is the absolute zero, right? Which we have not attained yet. So this T will be above zero. So both of them have opposite tendencies, this delta H and this delta S in a sense, right? And what we want to do is we want to minimize this. We want to minimize this, right? Delta H is enthalpy and delta S, guys, this is entropy, right? So these are two opposing factors, right? Between two opposing tendencies or factors, guys, the tendency to minimize this enthalpy, right? Instead of energy, I should write this enthalpy, right? A better term, all right? This gives free energy. This has to be minimized. This has to be minimized, guys, right? Also, at the same times, molecules try to maximize entropy. So they want to reduce their enthalpy and they want to maximize their entropy, right? Enthalpy and entropy, will be delving into it quite a bit. Just wanted to show you here how these factors play, right? So these are the enthalpy wants to be as low as possible, entropy wants to be as high as possible. So what happens is a compromise between them is reached, right? So a matter is not getting resolved, what would one do, right? Shake hands, right? What we can do about it, right? So something like that, they reach a compromise that okay, it's okay for me, it's okay for you, let's go ahead, right? So that sort of a compromise is reached in an equilibrium state, guys, in a chemical reaction or any sort of reaction, right? Okay, so I hope you understand this, and I'll move on to the next slide. Reversible reactions, right, can be established for both physical and chemical reactions, right? The reaction may be fast or slow depending on the experimental condition and the nature of the reactants, right? Very important experimental conditions, nature of the reactants, right, as well as the amount of energy being released or gained, right? So whatever the energy changes is happening is also very important. In fact, throughout your chemistry, this is very important. If you want to ace 11th, 12th and even beyond that, what you need is you need to see things on an energy level. So in the previous equation, the Gibbs-Helmholtz equation, delta G is equal to delta H minus T delta S, I showed you that delta G wants to be as less as possible. Delta G we have to minimize. Delta H wants to be as low as possible, but the entropy wants to be as high as possible. A compromise is reached in case of an equilibrium, right? Based on the extent to which the reactions proceed to the state of the chemical equilibrium, these may be classified into three groups, right? So extent of a reaction can be taking almost to completion, right? For an equilibrium, even for example, it might stop at 98-99%, right? When 98-99% of the reactants are utilized and products are yielded, they might be somewhere in the between, or the equilibrium might be reached very early, right? So guys, the reaction that nearly proceeds to completion, right? So for example, in a certain case, the reaction might complete by 98%, right? 98%, what that means is that the reactants have reacted 98%, only 2% of the reactants are left, right? And now products are in a great quality, in a great quantity, I mean. So what happens is the backward reaction rate is still very slow, right? The backward reaction rate is still very slow, even with the forward reaction, the concentration, I mean the number of moles left of reactants have become very low. Still, the tendency to go forward is the same as the tendency to go backward, right? So when the original reactants have become less, there will be lesser number of collisions, right? So when lesser number of collisions happening, there will be a lesser chance of chemical reaction happening in the forward direction. Still, it is as much as after 98% as the tendency to go backward, that is products reacting to form the original reactants. I hope you understand this, guys. The reaction in which only small amounts of products are formed, so this is the exact opposite of this. So what happens is no sooner as the reaction starts, all right, or a very little amount of the original reactants are used, the products have a tendency to go in a backward direction, right? So at 2% the equilibrium is reached and nothing is happening again, right? So no more new products are forming. So in this conditions, if you want new product to be formed, right, more product to be formed, we need to alter certain conditions like pressure, volume, temperature, perhaps introduce certain external factors to manipulate that equilibrium and drive the reaction in the forward direction. I hope you've understood this, guys. In which there is a third type of reaction in which the concentration of the reactants and the products are comparable, right? So they stop somewhere in the between. The tendency, so that means the tendency to go backward, the tendency to go forward is almost the same. It attains that equilibrium somewhere in the middle, right? When the concentration of the reactants and the original reactants and the products somewhere become comparable, right? I hope you understood this, guys. I'll move on.